Hey everybody, we're continuing with chapter 16 now, and we kind of started talking about some of the chapter 16 style reactions where you have a benzene with something on it, and then you're doing another aromatic reaction. And so remember, there's kind of like there's two things we're sort of going to talk about, I guess, and we already started talking about them a bit. The first thing is the idea of orthopara-direction and meta-direction. So if you have a substituent that directs to the orthopara-director or the meta-director, why does that happen? And we already started talking about that. The other concept is activation versus deactivation. Now these are related. Direction and activation are related, but a little different. Okay, and we're explaining this in the opposite order of the textbook. The big thing to remember, and this is all from last time, was that it's kind of an interplay between of electronic effects, induction effects, which are going through the sigma electron system, and that's kind of where you have like CHs versus CFs. The CHs can donate electrons, the CFs can withdraw electrons. Those are called inductive effects, going through the sigma electron system. And then when you have things that can form double bonds, like OCH3 or aldehyde, those are transmitting electrons to the pi system, and that's called resonance effects. So it's an interplay between inductive effects and resonance effects. Also from last time, we kind of summarized what are the common orthopara-directors, and we'll talk about the meta-directors this lecture. So the common orthopara-directors are things that, like a CH3 or other alkyl type thing, and those are all donating by induction. And then almost anything with a lone pair: oxygen, nitrogen, different kinds of nitrogen, even chlorines and bromines are all orthopara-directors. The funny thing is that these ones that, like the oxygen and nitrogen ones, are donating by resonance, while the halogens are donating by resonance, but withdrawing, electron withdrawing groups, by induction, because they're pulling electrons towards the halogen. So we kind of show it like, you're donating by resonance. You're donating by resonance while simultaneously withdrawing electron density by induction. You're donating through the pi system and withdrawing by the sigma system. And that's why they are donating by resonance and they're withdrawing by induction. And what you'll see, and we're going to emphasize this lecture, is the donation by resonance, just like you donate by resonance up top, that causes the orthopara-direction, OP direction. Okay? Whereas this withdrawing by induction, that causes deactivation. And deactivation just means like a slowed reaction. The reaction is a little slower. These top, everything but the halogens, are all activators, and that's due to the donation by induction or resonance. Okay, halogens are a little weird. All right, so the other thing was when we showed this, I'm going to show it again and step through it briefly. We showed this really cool diagram where we talk about the, if we have an electron donating group, and those are orthopara-directors. Everything is kind of explained by the carbocation intermediate. So if you have a donating group and you react with an electrophile, so the benzene attacks the electrophile can go to the ortho, the para, or the meta positions, right? So I'll talk about this last time. And then the issue is some of these carbocations are kind of stable. Like at the ortho position, the carbocation is directly next to a donating group. That's a really nice interaction. Same with the para. The only difference is you have to first resonate the electrons, and then you show, oh, that the carbocation is next to the donating group. But that's a positive thing. With a meta, you don't have that. No matter how you push the electrons, the plus charge is never adjacent to the donating group. It's always like next door. Okay? All right, so that was why, in a nutshell, ortho-para-directors are why donating groups cause ortho-para-direction. All right, so let's continue. And we're still on number 2, which is basically saying that electron donating groups are ortho-para-directors. We have a couple different kinds of ortho-para directing electron donating groups, but let's show a couple examples now. So first one I'm going to show is ethyl. And we're going to specifically show how is it an ortho-para director. And you know, on the previous page we said methyl, but I also said just alkyl in general. So an ethyl group is like a methyl group, and it does the same kind of stuff. So we're going to show those 3 situations again. We're going to show ortho, para, and meta. And what electrophile should we use? Because remember, if this goes back to chapter 15, you know, what are the reactions we know about? Well, there's like halogenation, nitration, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts isolation, all those things. And so we just pick any of them. The thing is, it's independent of the reaction. The effect is due to the substituent, right? So we'll do Cl2 FeCl3. All right, Cl2 FeCl3. Now we're not going to do the mechanism because we did that all in chapter 15. We're just going to draw the intermediate for ortho, intermediate for para, intermediate for meta. All right, so ortho. Ch2CH3, right? All right, so, and this all depends on how I drew the double bonds. So you want to be consistent with the way you draw the double bonds. The other thing is don't draw circles here, because remember, we can draw circles for benzenes, but that'll mess up our mechanism, because we got to show specific electron movement. So don't use circles, use double bonds, and be consistent, right? All right, so I'm going to put the chlorine, because this installs a chlorine, I'm going to put it right there. Assuming that's the case, what else do I need to draw? Well, the double bond on the left, it did not change. The double bond on the bottom right did not change. And what about the other stuff? Okay, so what is it? What else is at the chlorine? What else is at the chlorine position? Of course, there's an H there because there was a H before. There's an H after. Now, what else do I have to draw? Of course, a positive charge. And where's the positive charge? It's right where the ethyl group is. Okay, good. All right, and do we say this is a happy carbocation or a unhappy carbocation? So this is a happy one because the carbocation is stabilized by the ethyl group. The carbocation is stabilized by the ethyl group. You could also say it's a tertiary carbocation, right? You know, tertiary carbocations are stable, so that's stable and good. So maybe a little asterisk or star, maybe a smiley face, but that's a good happy carbocation. And then assuming the proton gets lost, because remember the last step of these reactions is the loss of the proton. I'm not going to show the mechanism just because of lack of space, but what's the product? The product is chloroethyl benzene, right? I'm just redrawing my ethyl as a line there. Of course, it's redraw CH2CH3, but that's the product, okay? And yes, this is favored due to the stability of the intermediate carbocation. Let's do the para now. Okay, I'm drawing a little small because of lack of space. So the chlorine goes to the para position. I'm also just going to draw my ethyl like that. Alright, are we cool? The other thing is, next thing is you draw the double bonds that did not change. Like the left double bond did not change. The top right, the double bond did not change. What else is where the chlorine is? H. And where is the positive charge? Maybe it's right there on the other carbon of the double bond. So draw our plus charge. Okay, and now you ask yourself, is this a happy carbocation or not? Or, I don't know. Well, it's not totally clear yet, so, because the plus charge is not next to that ethyl group, which would stabilize it, so you might resonate the double bond to push towards the that carbon bond, right? Can't zoom in too well. Yeah, so the double bond shifts one, and then that'll push the positive charge up to where the ethyl group is. Okay, and then we have a plus charge here. Double bond, chlorine, hydrogen. Yep. Ah, now we see the same thing that we saw above, right? Plus charge is next to the ethyl. Plus charge is next to the ethyl. And we say, ah, that's good. Star, smiley face. Good. So this is another good resonance structure. It's stabilized, and that's why it's, in addition to being an orthodirector, it'll be a paradirector. I don't need to draw the mechanism to the product, but I'll step through it in words. The product, of course, is the benzene, right? And the mechanism would be like a base takes the proton, and then electrons go to form the double bond, right? And then push one more to the positive charge. I'll draw it and I'll erase it just because I'm kind of lacking space here. So base would take the proton, push to the double bond, and then push up there, right? And that would generate the para-disubstituted product. Now I'm going to erase the mechanism because it just kind of distracts from the point I'm trying to make. I'm trying to really show the carbocation stability, and we did that. Okay, cool. So para is favored, right? So ortho's favored, para's favored. Let's do the meta. Okay, so ethyl up top, meta chlorine goes here. Of course, we see, look at the double bonds, you can see, well, where's the positive charge? There's going to be an H here, positive charge here. Okay, there we go. There's the carbocation. And just like we did before, now you can push, resonate. And you'll never see the nice complementary interaction that we saw before. So we won't see the positive charge be directly next to the benzene. There's always going to be one away. So it's not good. This is not a favored thing. If we do it again, if we resonate again, then the positive charge over here, it's this kind of unhappy state. You draw a smiley face. So that is why ethyl group is an orthodirector and a paradirector. Okay? And it's due to the carbocation stability in the intermediate, in the ortho case and the para case. Meta does not achieve that. Okay, another example. We'll do OCH3. Trying to fit in my ortho, para, and meta. I always do them in order, ortho, para, meta. Okay. Let's pick another reaction. What's another reaction to do? This time we'll do Friedel-Crafts Isolation. I'm just picking them. Any of them work from chapter 15. I'll give you a hint. It's going to be ortho-para favored, because we know this is an ortho-para director. Meta won't be favored. It's going to be very similar to what we just showed up here, this kind of analysis. Okay. So what metal? Is it iron or aluminum? You have to think back from chapter 15. For Friedel-Crafts, it's aluminum, so it's AlCl3. Whereas for chlorination, it's iron. Okay. So we draw the same intermediates. Alright, so OCH3. Alright, and then the ketone, the benzene attacks the acid chloride. Well, the mechanism was it makes that thing called an acylium ion. Remember that? Chapter 15? These react to make it acylium. We're not doing the mechanism though, we're just drawing the intermediate. So after that all happens and the benzene attacks, you get a ketone here. Orthoketone. Okay? We just ignore that top stuff for now. And where's the H? The H is here. Right. And cool. What are the double bonds that didn't change? There and there. Alright, happy or unhappy. Of course you can make a prediction and say, yeah. Oh yeah, we need the one other thing, the really important thing, what else should I draw? The positive charge at the carbon, right? The positive charge at the carbon. Okay? Alright, so is this happy or not? And of course that's a donating group. Oxygen has a lone pair, right? And the donating group can kick in and stabilize that positive charge. So yes, that's totally stable. Happy. We can draw a resonance structure of it. Okay. What does it look like? It's got the ketone over here, got the H here, double bond, right? And what does that oxygen thing look like now? It looks like O. I'll draw the CH3 up here. I just flipped it around to the other side. The OCH3. And where's the charge? Is on the positive charge on the oxygen. And yes, this is also a very stable, happy thing, right? Cool. So, of course, without showing the mechanism of the last step, it's the proton gets removed and the double bond, regenerate the double bond, kick the electrons onto the oxygen, and what's the product now? After all that happens, it's just going to be okay, it's a little smushed there, but yeah, it's a benzene, OCH3, and a ketone right there. And yeah, it's totally favored due to the stability of the intermediate carbocation. Para. Is the same. Okay, double bond, H, positive charge, okay, and now you ask yourself, is it stable? Well, it's not obvious, so you would resonate, and then when you resonate, then you see that you have that same thing where the oxygen can totally stabilize the carbocation, right? So we draw this thing again. Now it's OCH3, positive charge, double bond, H. Yeah. Okay. Same thing. as above, totally stabilized. It's an oxygen stabilized carbocation because you can draw a resonance of it. Alright, so it's a very stable carbocation. Plus charge. Okay, wonderful. Lose the proton. And that shows why the para one is also favored. Final product has the methoxy group and the ketone, right? Cool. Alright, so we showed ortho, we showed para. I'm not going to show meta. I'm going to let you do that one. So you can draw the meta. Do the same analysis that we've been doing. You can kind of look at the way we did the ethyl chlorine one, and I'll just say not stabilized, bad. But you can draw in the steps that are missing. Okay. Okay, so in summary, when we consider all of this, electron donating groups stabilize adjacent carbocations. And that's kind of our rationale. So we say, therefore, electron donating groups are orthopara directors. It's all about the stabilization of the adjacent carbocations. And electron donating groups do that on the ortho and the para carbons, but not on the meta. Okay, so that's a summary of all of this electron donating group, you know, the effect on direction. Okay. Okay, so the next thing we're going to talk about is how electron withdrawing groups don't do this, and that's going to be why electron withdrawing groups are meta directors. Okay, so number 3 is that electron withdrawing groups are meta directors, and let's list some examples of meta directors. We saw them before. Let's show them again. Maybe summarize these on an index card or something. But one of them was like a carbon with fluorines on it, trifluoromethyl, CF3. And this one we call an electron withdrawing group, EWG, by induction. Electron withdrawing group by induction. And the way it's an electron withdrawing group, of course, is you're pulling electrons towards the carbon, and that pulls them towards the fluorine. So it's like pulling electrons from the benzene. The benzene is the squiggly line that's attached, right? So then the other ones are a little different, but they're all like C double bond O, for example, aldehydes and ketones, ester, carboxylic acid, nitro, right? Sulfonic acid, S double bond O, double bond O, OH. All of these are electron withdrawing groups by resonance. Which again, the induction was the pi system, and the resonance is the, sorry, I got it backwards. Induction is sigma, resonance is pi system. So all of these ones, it's like the benzene, you know, it pulls electron density towards the functional group, and then it kicks up. It pushes towards the ketone and pushes up towards the nitro and pushes up towards the sulfonic acid and pushes up, etc. So you're making kind of like an intermediate double bond type species. That's why we say pi electrons, which is double bond. It's a little different than the induction because you're not forming anything that looks like a double bond for these ones. Okay? Cool. Alright, so why are these meta-directors? So we're going to do the same exact analysis that we did before, but for meta-directors. So all of these things that we drew above, we're just going to abbreviate as EWG. And we say, well, we react with an electrophile. These are all super electrophiles from chapter 15. You give yourself enough room. It's nice to draw this a little large. I mean, I should probably draw it larger, but on a whiteboard I usually draw this huge. But we got orthoparameta, yeah? Now we're going to draw what happens in the case of ortho. We know which is the good one, right? These are all meta-directors, so this will be the good one. There's going to be something really bad about ortho and paro. So if we have electron withdrawing group on top, and we got a electrophile there in the H, double bond, double bond. Where's the positive charge? Ah, it's right there. Right? Where it's at that carbon where the EWG is, right? Not on the EWG, it's on the aromatic carbon, right? So, is this happy or not? You have a positive charge directly next to something that's really trying to pull electrons. It's like pulling and pulling, and you're giving it nothing. It's like a black hole, right? So this is pulling, and there's nothing to pull. So what do we say? It's bad. So it's not going to happen. You're not going to get ortho direction with an electron withdrawing group. What about para? Okay, start with my EWG, then I fill in the double bonds that are not changing. So double bond, E, H. Where's the positive charge? It's always next door. Okay, is it bad, good, bad, or I don't know? The answer is I don't know, because you can't see anything really bad because the positive charge is not directly next to the electron withdrawing group. So I say, I don't know, and I'm going to draw resonance. So now we draw resonance, and we do resonance, and now we have EWG, double bond, we resonated the electrons to here. Now we have E and H. And where's the positive charge? Uh-oh. It's right there next to the electron withdrawing group. And you say, oh no, it's bad also. Okay? So this is explaining why these don't want to be orthopara directors, these electron withdrawing groups. Now we're going to do the meta. Draw the electron withdrawing group. Okay, so keep everything oriented the same way as before. Draw the E, the electrophile, and the H, and the double bond, and the double bond, and the, where's the plus charge? Now the plus charge is here. Good, bad, or I don't know. The answer now would be I don't know also, because you can't directly see anything bad about this or good or anything. So we push the resonant, or we resonate the electrons. HE. And and double bond we just shifted. So now the plus charge is here. Okay. And do we say good, bad, I don't know? Well, it's not good, it's not bad, it's still kind of I don't know, because the plus charge is not, you know, directly adjacent. So we say, well, I don't know, let's resonate again. So now I resonate again. And we push the plus charge to the other side. Electron withdrawing group, double bond, He. Okay, now it's like we pushed it everywhere we could possibly push it, and it's not bad in the way that these were bad. These had an EWG directly adjacent, and so I usually just at this point I say not as bad. It's not good, but it's not as bad as the other one. It's not as unstable. So of course the mechanism here is really easy. The base would just take the proton, take the electrons, and then our final product is the meta-directed product. Now we have the EWG up top, electrophile here. We say, oh great, okay. Alright, so now it's the product's meta-directed. Just like we said these are all meta-directors. Now we know why they're meta-directors, because ortho and para would be really bad. That's it in a nutshell. Okay. I like to state that in words also. I say EWG destabilizes adjacent positive charge. Carbocation. Right? Electron withdrawing groups destabilize adjacent carbocations, which creates a serious problem for ortho and para direction. Meta does not have adjacent carbocation. C plus carbocation, same thing. Meta does not have an adjacent carbocation, so therefore meta is favored. So hopefully that kind of explains why these electron withdrawing groups are meta-directors. Okay, it's kind of like just the opposite reasoning for why it's the opposite reasoning for why electron donating groups are ortho-para directors. Cool. Alright, so we're still on number 3, which is that electron withdrawing groups are meta-directors. We explained why they're meta-directors in general terms with our little figure. Let's show a couple examples of this now. So pick a meta-director. I don't know, what do you think? Any of those things we showed before, like ketones, aldehydes, esters, nitro, sulfonic acid, they all do that. So let's do a methyl ester. Okay. Now we'll pick one of the reactions we were doing, like nitration, H2so4. Okay, show our 3 cases, ortho, para, meta. And what we're going to expect again is that ortho and para are bad. They have an unstabilized intermediate, and then meta is not as bad. That's the way I like to say it. So I'm not going to show it all, because we've done this a few times now. Okay, so, oh yeah, what does this do? It attaches a what group? what, nitration? Remember nitration attaches a nitro group, NO2, plus charge. And of course we say, that's bad. You have a plus charge next to an electron withdrawing ester, right? It's trying to pull electrons towards the double bond O. So that is what we say is bad. Okay, so that's a bad carbocation. It's unlikely to go down this pathway. Para does the same. Okay, you don't see it immediately, so you draw the resonance structure, and then you eventually say, it's bad. And I'll let you do some of that work. Uh-oh. Okay, same thing, we draw the resonance structure to show that the plus charge is next to the ester, and that's bad. And meta, we do the same thing. So now the nitro is on the meta position along with the H. Where's the plus charge? Well, we look back and we see, well, based on this arrangement, that it's on the neighboring carbons. The plus charge is here. Okay. We do the same resonance analysis, blah blah blah, X, blah blah blah, Y. And we find that the same thing, that the plus charge does not actually wind up directly next to the ester. And so what do we say? We say not as bad. And we say that's generally considered good for these reactions. You know, if that's, if two things are bad and this is not as bad. And so the final product, after all is said and done, is, you know, I should show the resonance structures. I'll let you do that work. Yeah. And you get the final product. That's meta. Okay? We'll do one more. I'm going to really expedite this and let you do the hard work. Now that you know how to do it, let's draw another meta director. They all do the same thing essentially. Ortho, para, meta. So what's another one? Trifluoromethyl, CF3. Okay. And what's another one of these reactions? We'll do sulfonic acid, SO3 H2so4. Or sulfonation. Sorry, I'm kind of running out of space here. So if I do ortho, and remember, all I'm drawing is essentially the product with the functional group attached at the ortho position and para position, meta position. CF3, I'm just going to draw that out as SO3H, because that's the product, but what we're trying to do is analyze the carbocation intermediate. So, and for ortho, the big analysis here is, CF3 is a electron withdrawing group, right? It's got the delta negative fluorines. You have a plus charge there. You say, is it good or bad? That's really bad. So bad. Okay, I'm gonna omit these ones and say bad, but you can fill them in. You should fill them in. That's gonna be bad for para. And then the meta is not as bad. So it's not as unstable. And then of course the final product is CF3 S. Let's draw it out, the SO3H. Whoops. I was drawing ortho there. It's meta. That's the final product. It's meta-directed sulfonation at the meta position. Okay, cool. All right. Just for fun, let's think about a couple other little situations. What if you have an OCH3 and a nitro group? Whoa, that's going to get kind of weird, right? And we're going to do bromination on it. And, right, we're going to brominate this. How do you even, if you want to know what the product is, how do you even approach this? You're like, well, I think that is a what director and that's a what director. It's got lone pairs on it, right? If it's got lone pairs on the atom, you say, is it orthopair or meta? It is probably going to be an orthopara director, right? That's an orthopara director, and this is a what kind of director? Nitro, is it on our orthopara director list or our meta director list? You have to go look somewhere. And nitro, of course, is an electron withdrawing group. So this is an orthopara director, that's a meta director. Which sites does that suggest will get brominated? And remember, we need FeBr3 too. Where's ortho and para to this, and where's meta to this? Well, it could be this position, or it could be this position. And those are both in agreement with both of them. So this says orthopara, this says meta, and both of these are meta. So either of these is possible. Our two answers would be there's two possibilities, right? Where's the bromine potentially going to be? It's either going to be here or it's going to be here. And then just thinking about it, which of these might be more favored if you're considering sterics and, like, you know, congestion? Which one looks less congested, top or bottom? Probably the bottom. So if I was going to make a guess, I'd say probably the bottom one would be the more favored one, just in congestion, and that's actually a pretty good analysis. We'll talk more about this congestion issue in a bit. Let's just do one more like this, though. Just another example. As we work our way towards more complex problems. C triple bond N, now nitrile, C triple bond N. Okay. And let's do Hno3 H2so4. Okay. So this one's easier, right? First of all, you ask yourself, are these orthopara directors or are they meta directors? Well, this is easy because they're the same, and if you look in our chart, these are kind of like ketones and aldehydes and all those things, and these are meta directors, right? So they're both meta, so they're both saying the same exact thing. This is saying meta. This is saying meta. Of course, this one is meta to this as well, but this one can't like install something here because there's already the nitrile, right? These are called nitrile, remember? Nitrile functional group. Okay, so anyway, they're both saying here, right? That's where it's going to go. Now what's the reaction? It's nitration, so it's adding a nitro. So this is a very simple example. There's no competition or weirdness. Okay, let's draw the benzene. I'm just going to say CN and CN. It's the same thing, right? CN, CN. And where's my nitrate going to go? My nitro? Not nitrate, it's nitro. It's going to go there, so I'm going to say O2N. That's the product. It's a little bit of weird long bond because of the paper. Okay, but yeah, that's a pretty easy one, right? We'll see some more examples like this in a bit. Okay, so that was kind of a summary of electron withdrawing groups and how they cause meta direction. Okay, so we talked about how electron donating groups are orthopara directors. We talked about how electron withdrawing groups are meta directors. Now we're going to get into this whole activation versus deactivation thing. So orthopara versus meta direction. Orthopara, so we talked about this orthopara versus meta direction concept versus something else called activation and deactivation. So they're kind of two different concepts. Remember the book, I'm pretty sure the book sort of starts by talking about activation, deactivation, and then they move to orthopara versus meta direction. To me, it seems a little more logical to talk about direction first, so that's the way we do it. Anyway, this is not that crazy. This is almost easier of a concept. What do you think activated versus deactivated means? We talk about an activated ring and a deactivated ring. It has something to do with maybe the speed of the reaction. That's pretty much it. So, activated, do you think that's the fast one or the slow one? And deactivated, do you think that's the fast one or the slow one? So it's pretty obvious. Activated means fast. It's a fast reaction. Quickly. And a deactivated ring reacts slowly. Okay, so the meaning of the words makes sense, right? Now the only question, you could say that this is related to, so therefore it's related to kinetics. So the speed of the reaction reaction rates. Activated fast, deactivated slow. So in a nutshell, this is actually pretty easy. Think about a electron donating group. Electron donating group, it's attacking electrophile, right? In a nutshell, you can kind of think that the benzene's going to go attack, right? The benzene's a nucleophile, that's an electrophile. This goes and attacks, and the donating group kind of kicks down. And generally speaking, is this, do you get ortho or meta products? So, what do you think? Or think about what we learned. Do you get orthopara or meta? And it's orthopara. We talked about the kind of products you get for electron donated benzenes. Okay, and now let's talk about electron withdrawing groups, and then we'll come back to electron donating. Electron withdrawing groups do basically the same thing, right? You have an electron withdrawing group. You have a benzene, and the benzene's acting as nucleophile, it's attacking the electrophile, and what kind of products do you get? Here you get meta products, right? Okay, so that's what we've been talking about all along. Okay, so now which of these do you think would be kind of activated, like going faster? And it makes sense that if the benzene's a nucleophile and attacking, and you're donating electrons in, your thing is kicking electrons in, and it's going to go attack, that this would be activated. And because it's pushing electrons into the ring and they go attack, right? Pushes electrons into ring. Whereas the electron withdrawing group is kind of pulling electrons away. So is it going to be activated or deactivated? The electron withdrawing group is probably going to be deactivated. So it's pulling electrons away from the ring, so they're less likely to go attack, or it's just gonna be a little slower because there's fewer electrons in the benzene ring. And so yes, deactivated, and it's pulling, the electron withdrawing group is pulling electron away from ring. You could say that it's the benzene is less nucleophilic, decreases nucleophilicity of ring. Kind of makes sense, right? Okay, so that totally. I think that makes sense. That a donating group would be activated, an electron withdrawing group would be deactivated. But there's just a little twist to this. So let's review the different kinds of substituents again. And yeah. But basically what we're going to find is, for the most part, ortho-para directors are going to be activators and electron withdrawing groups are going to be deactivators. But we're going to find that this one instance of donating groups, certain donating groups are ortho-para directors, but are deactivators. And those are the halogens. So chlorine and bromine, they're a little bit electron withdrawing by induction, and that's why they become deactivators. Okay, so let's summarize all the different substituents one more time. So we're still on number 4, which is about activation and deactivation. So there's 3 kinds of substituents. 3 kinds of substituents. Ortho-para activators, meaning they direct ortho-para and they're activators. And that's like, we got OCH3, all the things with lone pairs on them. OH, NH2, amide, so NH with a C-double-bond-O on it. It's got a lone pair. Also things like CH3, alkyl. Could be methyl, could be ethyl. So the top ones are doing it one way, and the bottom is doing it a different way. They're all electron donating groups, right? They have lone pairs, except the bottom does not have a lone pair. So I say EDG by resonance. The bottom is EDG by, what's the other one? EDG, the I word, induction. Okay, so the methyl or alkyl is induction. Okay, then we have the meta ones. The meta ones are all deactivators. They're all deactivators. What are the... I'm going to draw it a little to the left. Okay, meta deactivators. Meta deactivators. They're meta directors, and they're deactivating, meaning they're a little slow. So what are the options? We have like nitrile, aldehyde, ketone, all of those kind of C-double-bond-O, C-triple-bond-N, nitro, SO3H, all of those kind of things. It's like one atom's connected to an oxygen or nitrogen or whatever. And then we have the other one, which is CF3. And we'd say the same kind of thing. Okay, so these are all electron withdrawing groups by resonance. And that explains everything. But these are not, this is not electron withdrawing by resonance. You can't form double bonds because you have 5 bonds to carbon. So it's just the fluorines are pulling on the carbon. This induction. It's going through the single bonding network. So these are electron withdrawing by induction. Cool. Okay, so then we have the third class that I was alluding to since the beginning of the chapter a little bit, is ortho-para deactivators. Okay, so and these are our halogens. The ones we really focus on are chlorine and bromine. I think iodine and fluorine do this too, but we don't see them as much. So these are a little funny. They're directing by resonance. So the lone pairs are kicking in. That's directing by resonance, and they're simultaneously pulling by induction. So they're pulling electrons outward towards the chlorine or bromine simultaneously inductively. So the way we just say that in words is they're directing by resonance, ortho-para directing. They're ortho-para directing by resonance, and they're deactivating by induction. So halogens are a little weird. Okay, so that's it in a nutshell. We have ortho-para activators, we have meta deactivators, and then the very tiny class of ortho-para deactivators. So they decrease the rate of the reaction a little bit because they're ortho-para directing by resonance and deactivating by induction. Okay. Alright, topic 5 is now going a little further into this. So what we're going to do is vary the extent of activation and deactivation. Using a couple strategies that we have. Yeah, so you're going to learn a couple tricks, yeah, to vary the extent of activation and deactivation, which is going to let us do some cool synthesis. So we're going to move to some neat synthesis of aromatic compounds very soon. I am going to say that the book goes into extensive detail. And we're not going to go into super extensive detail, so we're going to go into a little bit less detail, but we're still going to cover all the key tricks, alright? So if you're following along in the book, just realize it goes just a tad more into detail that we don't necessarily care about. Okay, that said, there's a couple like guidelines or tricks. Guideline number 1. First thing is that to know is that we have like 4 groups of activity order. What does that mean? Activity order? 4 groups. Now what that means is there's going to be like some substituents or groups are going to be more active than others. And we just do, the way we define this is this way. So there's 4 groups. The first group is the most reactive. NH2, OH. These guys are super, super, super active. We'll see how that applies in a little bit. They're the most active. The next level of activity are things like NH with an amide on it. If you're doing flashcards, this might be a good flashcard. Maybe each of these guidelines will be good flashcards, maybe. And then ether, so like a CH3 group or something. So OH is an NH2 are super active. Amide and ether are being like a CH3 or something. Those are going to be a little less active. Then we got the alkyl groups like methyl, ethyl, etc., propyl, and also halogens. And those are like the third group of activity. Okay, so these are going to be the most active. Next, alkyl and halogens have their own little group, and then the last one are the strong electron withdrawing groups, strong EWGs, which are all pretty much the meta directors. All the meta directors. So those are like, what do we got? Like nitro, CF3, ketones, all those kind of things. Aldehydes, etc. Okay? Alright, so we got 4 groups, and we're going to see how these groups apply in a second. Guideline number 2. First you got to know what the activity order. You're going to need to pretty much memorize these, so you might start doing that now. Okay, guideline number 2 is that the strongest activator wins in a competition. Strongest activator wins. So if you have a competition between these groups, strongest activator wins. Another way to say that is higher ranking groups override lower ranking groups. Higher ranking overrides lower ranking. Okay. So meaning, if I have, like, let's think about this case. OH versus CH3. This is a great first example. So if I have like 2 things on there, first of all, are they both the same kind of directors? What kind of director is OH? What kind of director is CH3? Well, that's an ortho-para director, that's an ortho-para director. So they're both kind of, saying, they're both saying ortho-para relative to each other, but one of these is super active and the other's not. So, who's the greatest activating groups? Like OH and H2. Okay, so the OH gets to decide. That's what I'm trying to say here. OH is the ortho-para director. Para is already taken, so ortho to OH would be like here or there, right? So where is whatever we're going to add, doesn't matter what it is, really, where's it going to go? Is it going to go to like this? These carbons are at the top are the same, bottom carbons are the same. So where's it going to go? OH decides, so it's going to be there. Left side, right side, doesn't matter, but it's going to be ortho to the OH. Can't be para because para is already taken. Alright? What about CH3NO2? Well, who's the greatest activator? Looking at the groups. Well, CH3 is definitely the greatest activator. The funny thing, though, is that this is an ortho-para director, this is a meta director. So there's actually not a competition. They're basically saying the same thing, because this is going to say ortho, this is saying meta, but meta is the same as ortho and the other one. So this one's actually a nice no competition one. Alright, what about carboxylic acid, NH2? Alright, so here's the greatest activator. Oh, NH2, totally. It's in the first group. So NH2 gets to decide. And it's an ortho-para director. So it's kind of saying ortho or para, but which is more likely, ortho or para, do you think? Ortho, which is next to it, so it's kind of sterically hindered, or para, which is out in space. So it's probably going to be para to that. Okay? Now this is also a case where even though this is the greater activator, this is also a meta director, right? So this is meta, that's ortho para. And so this, they're saying the same thing, and that's basically saying that position. Okay? Alright, and so there is this position, and I'm going to put it in parentheses because it's less likely due to sterics. Okay? And that's also, that would be meta to the carboxylic acid and ortho to the NH2. What about OCH3 methoxy and Br? Okay, this is an interesting one. This is definitely an interesting one. So this is yeah, this brings up a couple different points. First of all, who's the greatest activator? Methoxy, is it in the first, second, third, or fourth? It's in the second group, so it gets to decide. And the bromine is in the third group, so it's kind of the methoxy gets to decide. So this is a little interesting because what are the two options? I mean, this is saying orthopara, this gets to decide, so it's this position or this position. And now it actually does come down to a steric argument. Which atom is larger, or oxygen or bromine? If you look on the periodic table, bromine's kind of huge, right? It's lower on the periodic table. So this position is actually unlikely. This is going to be the one that wins. Okay, good. Now what about just one more? CN versus OCH3. All right, greatest activator wins. So this is a case. It's also going to be a case where there's not really competition because this is orthopara, that's meta. They're saying the same thing, right? OCH3 is in the second group. Nitrile is in the fourth group, and it's meta directing. So they actually say the same thing. It makes it easy. It's going to be right there. Couple more. Methyl, ethyl. Alright, who's the greatest activator? Well, they're both in the group 3 actually. Methyl and ethyl are both alkyl. So they're in competition. Neither of them is really a greater activator, but one's a little bigger, one's a little bit smaller, so probably going to put it right there next to the methyl. They're both orthopara directors too, right? Okay. Alright. Next one's really easy. If you ever have the option between like para directing or ortho directing, usually ortho is less favored. If you have the option. Due to what? If you have an ortho directing reaction and you have the option to go para, it's usually due to sterics. I'll just show two simple examples of this. So chloro CN. Alright, who is the greatest activator? First of all, chlorine is in the third group. Nitrile is in the 4th group, meta-directing. They're basically saying the same thing. Chlorine is an ortho-para-director. He gets to decide. So the options are basically ortho to the chlorine or para to the chlorine, and which one's going to win? That's going to be this one. Right? Because it's not next to the big chlorine, right? So that's one example. Here's just another interesting one. Okay, this looks weird, right? It's just it's a benzene with 2 oxygens and a little bridge. But it's just you know, you see these kind of things, and what's the activity? Well, who's the greatest activator, and which group are they in? They're like ethers, right? It's like a weird ether bridge. The ethers, of course, are in the 2nd group. Big thing, though, is they're both the same, so it's not like one wins over the other. So they're both saying the same thing, and they're both ortho-para directors, right? Because oxygen lone pairs. And so it's either going to be this position or this position. It's going to be para to either one or para to the other, which gives you basically the same product. I could draw the arrow there, I could draw the arrow there. But it's not going to be ortho to them, because ortho would be disfavored, right? Due to sterics. So yeah, it makes sense that it would be para to either of those guys. Alright, we're basically done. I'm just going to say that this last guideline is just a couple more examples, really, but the rules apply, all those rules we just talked about, for highly substituted derivatives as well. Highly substituted derivatives. These are all pretty obvious, I would say, so let's just show a couple more. When I say highly substituted, I mean a bunch of stuff on these benzenes. We'll even abbreviate the benzene as a circle at this point, it doesn't matter. Methyl, nitro, sulfonic acid. Okay, who's the greatest activator? Probably the methyl. And the methyl is an ortho-para director. And it's saying, well, ortho's taken, para's taken, so where's it going to go? It's going to go to the other ortho. So that's pretty obvious, right? What about CF3, chlorine, NH2, chlorine. Okay, who is the greatest activator? Remember our 4 groups? We're like, which one's the best of those? There's NH2, right? So it decides, and it's saying, I'm an ortho-para director, and the thing that we're going to attach goes para. Okay, so that's pretty obvious. Yeah, a little star, that's super active. In this case, the methyl, it's not a super active one, but yeah, sometimes helps to indicate it. This one is pretty obvious. OH versus OCH3. Pretty easy, actually. Who's the greatest activator, OH or OCH3? Go look at your chart. And of course, this is an ortho-para director. They're both ortho-para directors, but this is the greatest activator. It decides, and para would be preferred, so it goes there. One more. OCH3, isopropyl, OCH3 versus isopropyl. Look at your chart. Look at your chart. This is the 2nd group, right? The ethers are in the 2nd group. Alkyl is in the 3rd group. So ether wins. It's an ortho-para director. So where is the thing going to go that we're attaching? Probably ortho to it because para is taken. Okay. All right. So we're done. What I'll tell you, what we're going to do next is synthetic strategies. I'm just going to give the name of it. synthetic strategies toward substituted benzenes. So this gets fun. What we're going to do next is strategies, synthetic strategies, to start building complicated benzenes. And I'm going to tell you how to do it with these strategies. So that's the next topic. All right, cool. See ya.